our last video, we introduced the amplifier bias current and showed that in a very simple case, we can just connect a resistor between that input and the control voltage, and that will allow us to control the gain of the OTA with the voltage. However, this has a number of problems. It lacks high accuracy, it's not particularly flexible, so in many cases we need something a little bit more robust than a simple resistor. In general, the way to do this is with a current source. Here we will consider a very basic current source. Note that for special purpose applications you may need something considerably more complicated than just a simple current source. For example, in electronic music we often need to do an exponential conversion, meaning in this case that we need to take a linear control voltage and convert that to an exponentially related current. But we will look at exponential converters in a later series of videos. In our study of op-amps, we saw very early on that it's easy to convert a voltage to a current. The problem with that is that all of the current goes into or out of the op-amp output, meaning that somehow or other you've got to connect that OTA directly to the output of the op-amp. In other words, the OTA has to be in the feedback loop. It's not obvious how to do that, and in fact that's not what we're going to do here. There is actually a way to incorporate the OTA as a feedback component, and we might look at that case later on. It's sort of an interesting little trick you can pull. So what we need is we need to get the desired negative feedback and yet not steal all of that current to pump back into the operational amplifier. We need that current to go somewhere else, specifically to the amplifier bias input. A bipolar junction transistor can easily serve this function. Typically, the collector would be the terminal used as the current source itself, and since we need a current source, not a current sink, then a PNP would be the appropriate type of BJT to choose. If your transistor has a fairly high gain, then the amount of current stolen from the emitter current to go into the operational amplifier is very small, and so almost all of the emitter current ends up popping out of the collector and then onto our amplifier bias input. Now note, if the current drops too low, since none of it goes into or out of the inverting input of the op-amp, it all goes through that resistor. If the current drops too low, the voltage at the inverting input, which is supposed to be a virtual ground, has to go up. If that voltage goes up, since that's the inverting input, then the output is going to start going negative. Now, if that goes negative, that's going to increase the emitter to base junction voltage, which is going to increase the current until you restore your virtual ground. If the current gets too high, you have exactly the opposite situation. The output voltage goes up, meaning it's going to decrease that current and again restoring the virtual ground. In normal operation, the base voltage will be slightly below ground, one diode drop below ground, so somewhere around half a volt. It depends on the current you're running. And since the amplifier bias input is way down there near minus 15 volts in our case, then the collector to base junction remains reliably reverse biased, the transistor stays in the active region, and all is good. Now, this very, very simple current source does have a few problems. If V sub C goes negative, that transistor can't conduct current in the opposite direction, which is what would be required in this case, and so the op-amp is going to peg itself to the positive saturation voltage, somewhere up around 14 volts. One thing to note here is that we may want that current to go to 0 to make the gain of the OTA go to 0, and that means we've got to bring that control voltage down to 0, and it's really difficult with a variable voltage to get it exactly 0 volts, so you're likely to go slightly negative, so you're likely for that op amp to go into positive saturation. This is immediately a problem, because if you look up the specifications for most small signal transistors, you will see that the maximum reverse bias across the emitter to base junction is usually about 5 or 6 volts. However, you've got a voltage on the emitter that is at least slightly negative, and you've got about 14 volts on the base, and so you've got 14 or more volts of reverse bias on that transistor. That is way over the absolute maximum, and that junction is going to go into reverse breakdown and start conducting, and that is not what you want. You might destroy the transistor. It just depends on a number of factors, but in general you don't want that to happen. So that's one problem we need to solve. Also, do note that the actual current going to the OTA is a little bit less than the current set by that resistor. Now, in some situations, that difference is probably negligible. In very demanding situations, you may really want those two currents to be the same. So that's another problem we need to address. But those problems are going to have to wait, guess what, until the next video.